Hello, today we are going to learn the C programming language by looking and understanding the C programming language examples from the book Thinking in C: Foundations for Java and C++ by Bruce Eckel and Chuck Allison. Let's prove that our integrated development environment for C works correctly. We've created a hello world C programming language, put a breakpoint in here. Let's start the debugger. So the debugger has stopped on line 5. This is how the program that's generically called hello world looks like for the C programming language. We have one top level free function which has a special name, main. Might have parameters or not. In this case it has no parameters. Might return void or nothing, or might return an integer, which is the case. If it returns an integer, then this return is the exit status of the process. 0 is the successful exit status. Anything else than 0 means that the process has finished incorrectly or crashed or had an issue. Okay, let's look at the application output. Where is it hidden? So the string hello world is printed to the console, to the standard output of this process, but not when we get at line 6, somewhere after that, because there's synchronization at work there. So let's start debugging again. Let's look at the shortcuts. So we have step over F10, and this is the integrated development environment Qt Creator running on a Linux operating system, Ubuntu 23.10. So F10, nothing is printed yet to the standard output, nothing. And at some point, while the program is finishing, is going to actually sync and write to the hard disk, to the standard output. Okay, so we define a top level function. We return 0, which is success, which will mean the process has finished successfully with exit status success, which is 0. But then we're also trying to write to the standard output to the console. For that, we're going to use this function that's part of the C programming language standard library and defined in here. So this is a C programming language include or header file. This is the full path of the file /usr/include/stdio.h. std means standard, io means input output, so writes to the standard output stream to the standard error stream, or reads from the standard input stream, or reads from the keyboard, or writes to the monitor. Let's see how this file looks like. These are C programming language include guards, such that you don't... Where is it? Such that you don't include this file stdio.h twice in your translation unit. This file is cross-platform, runs on a variety of operating systems. That's why we have macros which do different things on different operating systems. Let's look at the structure of the file. There's a ton of free functions. Okay, we'll ignore the include files for a while. we'll just know that whenever we want to use the C programming language standard function printf, we'll always need to include the stdio.h file by having such a line at the top of the translation unit, or at the top of the file with the extension .c. So this pound hash sign, and then include, and then space, and then between angular parentheses, so less than and greater than stdio.h. Now we're at the very first source code example in the book, Thinking in C, where we have again include stdio.h. This is a single line comment. This line is actually ignored by the C compiler, doesn't do anything in the final process and program. This is a source code file. From it, the compiler will generate an executable file, and then we'll run that executable file as a process. So there's three entities: the source code file, which is called main.c, the executable, which is probably going to be called main, and then the process, which has a process ID and runs on our computer. Let's again start with a debugger. And now we're going to look at the three entities. So the file, the executable is actually called proj. It's this one. Let's see how it looks like. So it's an executable file owned by me. Of type ELF, so this is the Linux executable binary file format. 64-bit because I'm on x86 64, which is AMD 64, which is the Intel or AMD normal CPU, central processing unit. So I'm on a normal desktop computer. Okay, and we can run this executable either by providing the full path like this, or by changing into its directory and then running the executable like this, or we're inside of the debugger and the Qt Creator integrated development environment for the C programming language is actually taking care of running the process and notifying us when the process has ended, so managing the life cycle of the process. So actually the process GDB, which is the Linux standard GNU project debugger, is running the process proj. So the process proj is actually a child process of the parent process GDB, which is then run by Qt Creator. So Qt Creator is the parent process of this GDB. Okay, so our file has again just one free function, top level, with the same special name, main, 0 parameters, and returns integer, returns 0, which is success, and then uses puts to write to the standard output twice. Let's see how it does that. F10 and then F10. Again, we won't see the output until at some later stage. What puts does is writes a string followed by a new line to standard output. So it writes to the console or to the terminal the value of the parameter, which in our case it's a literal string, and then puts a new line. I do not like the fact that when I use print for puts, I cannot immediately see in the standard output the value of the string. This is because the operating system tries to be intelligent and will try to cache the fact that we want to write something to the standard output, and it will delay performing that action until when it's absolutely necessary. So what I want to do is tell the operating system, hey, don't have any caches between this process, which is called proj, and the standard output. So for that, I searched on the internet, could create a debugger see immediately print output, because that's what I came up with as a search query for Google. And it tells us in here what the problem is that sometimes when you print text without a \n, the text will not immediately be flushed to the standard output. Sometimes it will not be flushed to the standard output, not even if you put a \n, which is a new line character. And then it takes us to a Stack Overflow thread. And in here we find out that the standard output is a special stream because it is buffered by default. What we want is to tell the operating system and standard output, hey, please, I want standard output streams to not be buffered. And we could either not use the standard output stream, use the other standard stream, which is the standard error stream. I do not want to do that. Or each time I do a print or a puts or something, I need to go f-flush std out. So that's mega tedious. I will need to add this to many examples, and I do not want to do that. Or we can say disable buffering on standard output for the duration of this process using the setBuff standard C programming language function. So let's use this one. So setBuff and then std out and then null. Let's look at the documentation. And in the documentation it says if buff is null, and it is, so the second parameter, this thing, then make the stream, which is the standard output default standard stream, unbuffered, which is exactly what we want. Buffered means that if you write something to that stream, the action will complete sometime in the future, whereas unbuffered means if I write something to the stream, then everything happens immediately. No delay. So that's what I want. No buffering, no delay. Let's now run the process again. The debugger. Let's clean the standard output. We do not want this for now. Okay. So it immediately writes to standard output each time we call the function puts or printf. Okay, puts means put string, and printf means print formatted. The second source code example from the book. Let's look at it. Let's run it with the debugger to understand it better. So it says puts, which will write to the standard output. F10, step over to go from line 11 to line 12. We can see that it wrote something to the standard output, enter the first number. And now it's using the other type of functions from standard input, not ones that do output, but ones that do input. So scanf means that it's waiting for me using my keyboard to enter a decimal, which means an integer, which means a negative integer 0 or a positive integer. Okay, let's skip over this line. So let's go from line 12 to 13 by pressing F10. And now there's no cursor in here. It's actually waiting for me to enter a integer value in here. So let's go with 3 and then press enter. Okay, so you need to configure the integrated development environment Qt Creator such that it takes the standard input from the terminal and gives it to the process, to proj. You do that from the projects mode control 5 and then run, and then this checkbox run in terminal. Let's see how it works. Let's stop the debugging. Where is that? And then let's start the debugger. Okay, so F10 just writes something to the standard output. And now it's waiting for me to enter a number. Let's go with 3. Press enter. And now the focus has moved from this tool window at the bottom of the integrated development environment to line 13, where we can see the cursor, and we can also see this arrow facing rightwards, which shows us the line where the debugger is currently paused. Okay. What did scanf do? It took the characters that I wrote at the terminal. So it's just a 3 and an enter, a new line. It ignored the new line, and what was before it, so just the character 3, was converted to %d, which means decimal, which means integer. And now the integer 3 is stored into num1, which num1 is a local variable. There's 3 local variables. 2 will be of type integer, so will not have anything after the decimal comma dot, whereas this has an integer part and something after the decimal dot. It's a floating point number type. Okay, so in the local variable num we have the integer 3. We'll put another integer into the second local variable of type integer while we run line 14. So now we're at line 13. Something will get written to the standard output, which is enter the second number. After we go over line 14, it's going to jump over line 15, which is empty, go straight to line 16, and in meanwhile will wait for me to enter an integer from the keyboard. So let's make this 4. Press enter. So the terminal will wait for me to keep entering integer characters on my keyboard or press enter. Now I have pressed enter. Again, scanf looks at whatever I entered using my keyboard. So I put in, I pressed the keyboard buttons 4, 1, 2, 3, 4 and the enter key. It ignored the enter key, looked what was before, so it was 4, 1, 2, 3, 4, which it then converted to integer. So that's the integer number 41,234, and has stored this integer value into the local variable num2. Okay, now we're at line 16. Line 16 was not executed yet. We're just before executing line 16. We'll go at line 17 by pressing the button F10 or step over or step over. So let's use this button this time, step over. It has finished executing line 16, which has the integers num1 and num2. The result is 41237, and that integer value is now stored into the local variable of type float named sum. Okay, so this sum can store inside the value 0.7, whereas this can only store the value 0 or 7. It cannot store decimal places 0.7. Okay. And the value of sum of the result of adding 3 to 4, 1, 2, 3, 4 will be printed to the standard output, to the console, to the terminal, using the printf domain-specific language. So this is an entire programming language in itself, this one and this one, which uses placeholders. %f means floating point, %d means integer. So it takes the sum, divides it by 2, and will be something with dot 5 at the end. And then that number is going to be printed, put inside of this, instead of this placeholder. And then \n means put a new line character to the standard output. So to the standard output, the following characters will be printed: uppercase T, lowercase h, lowercase e, space, a, v, etc. And then space, and then this will be the value of sum divided by 2, which we do not know yet which it is. Let's find out. So the value is, how do we copy this? Says in here. So 41237, and then divided by 2 is 20,000 and then comma 5. Okay. And that's what it is, 20,000 and then decimal dot and then 5. And after all of these zeros, a new line character was printed. That's why the terminal has now advanced to the next line. Okay, after line F18, the main function will exit, which will close the process. F5. Next up is the limits.c sample file, which shows us for the built-in C programming language types char, short, integer, and long integer, the maximum and minimum possible values. So these are signed types, not unsigned types. So unsigned types have the minimum value 0 and then go from there. They're all positive. Whereas signed go to minus something and then plus something. Let's actually run this entire program. So the built-in integer types used by the programming language C are long, which is long int, and then int, which is integer, and then short, and then char, depending on my operating system, depending on my central processing unit, and maybe on other things, maybe on my compiler. These will have different values. These are the values that work with my combination of Linux operating system plus GCC. So I'm searching for C language integer types, and I get to the Wikipedia page, C data types. The integer data types for the C programming language are defined in the C programming language standard. And maybe the C programming language standard is not that easy to read. And I myself do not know exactly what these values are on the different platforms. So it says that a char type, which we have in here in our example, has minimum 8 bits, and char min, char max in our case are minus 128 and plus 127, and then there's the 0 value. Okay, so that's for char, which is the same thing as signed char, containing at least this range. Okay, then there's short, which is the same thing as short int or signed short int, which has minimum 16 bits and at least this range. So exactly this minimal range is available on my compiler, and exactly 16-bit. Okay, then there's the integer, which is signed or signed int. So this is the name of a type, and this is another name for the same type, and then this is another name for the exact same type. At least 16 bytes, at least 16 bits, okay, and at least the same range as short int, but it's larger in my case. So I'm not sure what this thing is, probably 32 bits. And then long, which is the same thing as long int or signed long int, should contain minimum 32 bits. This range, I can see it for the integer in my case. So now we know that integer is 32-bit and has this range. And we just found out that 16-bit has this range ending with 807 and starting with -9. So this is 64-bit on my combination compiler operating system CPU architecture. And now the same thing for the floating point types. We're just going to run this. So says that there's 3 types that have a decimal point. So that's float, double, and long double. Maybe there's even more in the C standard library. And these are the minimum and maximum number that can be represented on these 3 types. But then not all of the numbers that are greater than this value and less than this value can be represented as a float. Because there's an infinity of numbers between -1 and +1 if you allow the decimal point. The next source code sample. Let's see if this thing builds. So it doesn't like the fact that the top level function doesn't define its return type, might be void. Let's build and let's just run it. So let's see what this program does. It has 3 local variables. Then it's using a single printf statement. Again, this is a domain-specific language. It's an entire programming language in itself. These are new lines, which is this character, and then this character, and then this character. And this is \f. This expects a variable of type float, which it is. Print it here. Then another variable of type float, this thing here. And then a variable of type lf, which I'm not sure what means, long double or something, which z is a long double. Okay. So there's a conversion from unsigned long int to float. And it complains that the value has been changed, does not end with a 5, now ends with a 6. Because this number cannot be stored as a float. Okay. And then this does the same change where it changes the last digit from 5 to 6. So be very careful when you're working with very large numbers, with numbers that are close to the edge of the range of allowable values in a data type. Okay, the next example. I have run the example. This is what's written to the terminal, to the standard output, to the console. We have 1, 2, 3, 4, 5, 6 printfs. Each ends with a \n. And then we have 6 lines printed to the standard output. And it's doing bit operations. Short int. In this case, it's 2 bytes, which is 16 bits. Yeah, so integer is 32 bits on my machine. Short int is 16 bits. So this is how the bits of the local variable n look like. Everything's 0. and then 1 0 1 0 0 1 and then 0 0. This is hexadecimal, so base 16. This is binary, so base 2. Okay, so it takes these bits and then these bits and does a bitwise AND operation, which means if this bit and this bit is 0, it will generate a 0. If this bit and this bit are both 1, it will generate a 1. 0 and 0 will be a 0. 1 and 1 will be a 1. 0 and 1 will be a 0. 0, 0. So the only case where it generates the bit 1 is if both the bit from the first operand and the bit from the second operand are 1. So it's actually everything's 0 in the result except on positions this, this, and this on 3 positions, which gives A4 in base 16. Okay, so this is bitwise AND, bitwise OR, bitwise XOR, bitwise negation, and then shift bitwise operations. 3 to the left and 3 to the right. Okay. Next up, age.c. Comments on your age. Okay, what does it do? You provide an age at the command line, and then it uses alternative structures, which is if, else if, and else blocks. So this is a then block, then block, then block, then block, and an else block. And then block and else block. To write text about your age. Okay, so let's start the debugger, put a breakpoint somewhere in here. So says enter your age, and I'm going to lie. Okay. So age is 19. If age is less than 20, then I'm a youth. Okay, so it writes to the standard output youth. These, and these will not be evaluated, and it will jump straight to the end of the process. Okay. What about age less than 80 but greater than 60? So that would be 65. So age is 65. And it's the 65 is not less than 20, not less than 40, greater, not less than 60, but less than 80. And in this case, it's golden. Okay. And if I'm 85, it will enter this else block. So let's make my age how do I actually do it? 87. Let's move the breakpoint here, not here. So the process will start, will wait for me to enter the number, and then will break on line 11. So 87, not less than 20, not less than 40, not less than 60, not less than 80, but something else. So which means greater than or equal to 80. Says, are you really 87? And then I need to confirm that thing using an uppercase Y or a lowercase y. I'm going to answer with uppercase N. Okay, so really contains just one character, not one string, one character. And the character is uppercase N, and that character is different from uppercase Y or lowercase y. The condition is false. We're entering this else block, which is not surrounded by curly brackets. And it's going to write to the terminal, I don't think so. I didn't think so. Okay. Clever. Next up, we have the same program written in the C programming language, but it's not using if alternative structure. It's using the alternative structure switch case. So we want to put a breakpoint after the scanf, so on line 10, and start the debugger. It asks, so these parts are the same, and the bodies of the branches are the same. So this was a then branch, and now it's inside of the case 0 block. This was the first if-else if then branch, and now it's in the block of the case 1. Okay, so we're on line 12, which means it's before line 12. It's waiting for me to enter the age. So let's go again with 88. And it's taking the age, dividing it by 20. So in this case, it will be an integer division. It will be 4. So not 4.4, but 4. Okay. It jumps straight into the default block because age divided by 20 is 4, which is not 0, not 1, not 2, not 3. Any other value for age divided into for the result of the binary operation age integer divided by 20 will jump to this block. And then we saw this block previously. So are you really 88, and then scanf waiting for just one character, which should be lowercase n in this case, and n is different from uppercase y, different from lowercase y, so it will not enter this then block, will enter this else block. Okay, that's it. Next up, let's see what does this program do. It's building. And now it's waiting for me. It doesn't say what I should enter. So it should have had a print instruction for me what I should click on which button I should press on my keyboard. But I can see in here it says \d, which means any integer would do. So let's go with 23. And it will return 1 if it could put a value into n. I'm not sure what this equals to 1 does. Where do we have its help? We don't have any help, so let's search online. Okay, so I'm searching for the C programming language and then scanf. And one of the websites that I have used previously is C reference, so c++.com/reference. Reads data from standard input, so from my keyboard in this case. Stores the data according to the parameter format, which is the domain specific language, which in our case just says any integer would do. Okay, but then what is the return value? Now it says about the format parameter, defines the domain specific language, and return value. On success, the function returns the number of items of the argument list successfully filled. So if there's more items to be read, and it's just one, so just one local variable to be read, then it returns a 1. Okay. So in this case, the number that was read is 23, shown in here. And we're going to compute evens and odds, not 0. If you do modulo 2, which means the remainder of the integer, the division by 2, integer division by 2. So 23, integer divided by 2, that's 11, and remainder 1. So enters the case 1 because the remainder is 1. And there's the O sum. So the O sum is in fact the count of odd numbers. And then there's the count of even numbers. So don't name the local variables with so bad names. Very, very bad names. And n also is not clear what it does. So let's actually fix this sample. Let's see if we have a refactor in here. Rename this thing. So this is count of odd numbers. Okay. And this guy is count of even numbers. Okay, and this n is the current number. Okay. Let's do another example of a even number, 4. So 4 is not 0. And then we do integer division by 2, that's 2, remainder 0, modulo is 0, so it will go to this block. Count of even numbers is used to be 0 and now it's going to be, no, it's sum of even numbers because it goes 0 plus the entire value of the current number, which is 4. Okay. Let's rename this thing again. Okay, and now let's just run the program. That should be enough. So first number 4 and 6 and just one odd 3 and then some other characters than an integer and press enter, or just press enter. Sum of evens plus 6 plus 4, that's 10. Sum of odds, just 3. So that's how you would read a list of numbers from the terminal. Does not matter what is the length of the list, how many numbers you want to read. Reading will stop when scanf cannot put a valid value in here. So I put an A in here, which is not a valid integer. This was 0. 0 is different than 0, so then the entire while block has finished. Let's see this in action. So we are going to provide a even numbers. Let's go 3. Another even number. Let's go 5. And now we want to stop the iteration. We're going to just press enter, not provide anything. It still waits for me to enter something. So let's go with the text exit. Press enter. Okay, so scanf has returned 0. 0 is not 1. This condition is not true. The body of while cannot be evaluated again. So it jumps to the line 28, which is empty, so goes to line 29. No evens and 2 odds. 8. Next up, we have the same program as before, but we're using a for repetitive structure, not a while repetitive structure. So there's no initialization, no change, and no condition. So this is an infinite for loop, repeats forever. And then when we decide enough is enough, we use the break statement. Break will exit the repetitive structure. This break will just exit this case. This break just exits this case. Whereas this break inside of this then block exits the parent repetitive structure. So let's see how that works. Put a breakpoint. Enter an integer 0 to quit. 0. So 0 was provided. The local variable n has value 0. The condition is true. The then block is evaluated of this if alternative structure. And this break jumps to line 31, so outside of the block of the for. Both sums are empty or 0. Let's run it again now with correct values. So let's give 2 evens 50 and 20. And now we're going to give a 0 to exit. So n is 0. Does break. and straight to line 32. Okay, sum of evens 50 plus 20 is 70, sum of odds 0. So this resembles the not structured programming that you can do with the C programming language instruction goto. Where you can, with goto, you can jump to a label. You can put a label on any line, source code line, and that will jump there. Okay. I do use break, continue, whereas I do not use gotos. So this would be an example of the goto statement. We have two labels, G colon and S colon. So the execution goes like this. We have a local variable age. We read the age. If age is 17, that's not greater than or equal to 18. This block will be run, which goes to S. So jumps straight here to the print line. The next instruction that we are going to use with repetitive structures is continue. So we had break before, and now we have continue. Break jumps out of the body of the for and out of the for instruction. So we'll jump to line 28, whereas continue will skip the rest of the body of the for and go back to line 15, where incrementation takes place and then the Boolean condition is being evaluated. Let's run and see. So we have a size which is 5, an array of integers with these values. We have a local for iterator variable, which is this I, which goes from 0 and then stops before 5, so from 0 to 4, and then pre-increment. Okay, so I is 0, 0 is less than 5, and then it takes the nums of I, which is nums of 0, which is the first position, the integer at the first position in the array nums, which is 10, okay, and then it divides, that does integer division by 2. If it's 0, that means it's no, this is modulo, yes. So it does modulo. For evens, the remainder of the integer division with 2 will be 0, so the modulo, mod 2. And for odds, the mod 2 will be 1. So all of the evens will be skipped exactly how it says in the comment. The first one is 10, is a even, and we will skip. It enters the block of the then of this if statement. All of these lines will be skipped, and the debugger will go to line 15. On line 15, this instruction has been evaluated a while back, and now these two will be run. So first it increments and then checks if the new value of I, which is 1, is less than 5. And it is. So I is 1. Okay, this one is the second value in the nums array, which is nums of 1 Mode 2 is 1 because it's an odd. It will not enter the then block. It will go at the instruction 20, which is the one after the if statement. So lines 80, 18 and 19 are the alternative structure if. So we're at line 20 now. Digit 2 is a local variable inside this, the body of the 4 will be the remainder of division by 10, so 0 to 9, and it's 1, of course. And then 21 integer division by 10 is going to be 2, so dig 2 is 2. Okay, and then it goes 1 plus 2 is 3, it's not 7. Okay, the one that will be found is 4 plus 3 is 7, and it should be odd because otherwise it's going to be skipped. Okay, so 32 is even, will be skipped, and 43 not even, and 4 plus 3 is 7. It will print found 43, and then this break will exit the repetitive structure 4 and will go to line 28. Where are you? And that's it. Next up, we have, previously we had the array of integers of just one dimension. Now we have an array of integers of 2 dimensions. So on the first position, there's this pair, 1 and 2. On the second position, there's this pair, 3 and 4. And on the third position, there's this pair, 5 and 6. So this is index 0, index 1, and index 2. And then each of these 3 items on index 0 to 2 have 2 positions. Positions are 0 and 1. Let's debug. We have a 2-dimensional array. In order to parse it, we'll need an index that points to this item or to this item or to this item. That's going to be index I. And then we need, for each of these 3 pairs, an index that goes through the elements of the pairs. So that goes 0, 1, 0, 1, 0, 1, and that's going to be j. This is commonly done, like you see in here, with 2 repetitive structures, one for these items and another one inside of the first, which goes like this. And then at the next iteration of the exterior 4 goes like this. And then at the next iteration of the exterior 4, it goes like 5 and 6. Okay. The indexes are correct. So for the interior 4 structure, we have j going from 0 to 1. And for the exterior 4 repetitive structure, I goes from 0 to 2, which is correct. Okay, so we have I is 0, j is 0, and a of 0 and 0 is this 1. Okay, then we have I is 0 and j is 1, which means this is I0, this is j1, so 2. After it finishes the interior 4, we put a new line. So now we're on this line. Okay, now we're at 1 and 0. So I1, J0, which is I1, J0, 3. This is 1 and 1, so this is 1 for the I and for the J1. That's 4. Then a new line, and then the rest, which is I is 2, and J is 0 and 1, so 5 and 6, and then new line. Okay, so previously we had a two-dimensional array of integers. This is a three-dimensional array of integers. You can have as many dimensions as you want. So there's 1, 2, where is it? This is the first item, this is the second item. And inside of the first item we have 1, 2, 3 items, and in the first item we have the first item and the second item. For that we need 3 repetitive for structures with iterator variable I, J, and K. This is done commonly, often used. We have a print f and then 2 new lines being printed to the standard output. Now on line 8 and 9, the 3D integer array is being defined. We're inside of the first for block, inside of the second for structure, the one with J, and inside of the third for repetitive structure, the one with K. This body of the innermost for loop has just one instruction, line 17, which prints just one item with indexes I equals 0, J equals 0, K equals 0. So that means this is 0, the first item. This is 0, the first item, and this is index 0, the first item. Okay. So the interiormost for structure, the one with K, goes from 0 to 1. So the body of the innermost for is run twice. Okay, then we're now out of the for with K and into the for with J. Put char writes a new line, and then J becomes 1. So J1, I0, and then this is going to be run twice. At the end, a new line, and then J will become 2. So I1, I0, J2, and K0 and 1. New line, and then J cannot become 3. We are going to print a new line. So we're done with all of these part. I will become 1 and we'll do this part. So now I is 1, which means we'll print all of these 3 pairs with new line as separator. And that's it. Next up is this linear initialization of a multi-dimensional array, where it says that we can keep all of the C programming language instructions unchanged except the one where we declare and define the three-dimensional array. So all of these parts are identical. What's different is the fact that just a simple list of integers is provided for initialization, not these pairs in pair in pair. So let's see if it actually works correct. Start debugging. And let's look at A. So it's the same, has the same values as previously. The same things will be printed to the standard output. Next up is a program that reads an array of integers and then prints the integers in the reverse order in which they were read. So let's see. So step when 0 is found, there's size 20 for the array. Let's run it first without or not. Okay, so now I should enter an integer. Let's go with -1. Different than 0, will not break. We'll put in the array nums on the first position the -1. Then I'm going to put a 10. So anything but 0. Any integer except 0. 3. And now we'll put a 0. So 0 is equal to 0. We'll break, we'll go to line 21, which is empty, so it will go to line 22. Let's look at the nums array. So there's 20 positions, position 0 to 19. The values on the various positions are not known. For instance, on position 19, there's this 32,000. On position 18, there's 71 million. The only thing that we know is that we have read n numbers, which n is 3, and the first 3 positions in the array were actually introduced by me using the keyboard. So -1, 10, 3. The others are not initialized and do not matter. Okay, so this is a 4 from 0 to at most 20, so stops before 20, which is 19. This goes upwards from 0, 1 to 3, whereas this 4 goes downwards. So it starts from n, which is 3 minus 1, 2, and goes to 0, descending. So 2, 1, and then 0. I first is the first the index that's the biggest, which is index 2, where we have a 3, which gets printed. Then I will be decremented. Was 2, now it's 1, but 1 still is greater than or equal to 0. We'll print nums of 1, which is the second value that I have introduced, which is the 10. I will be decremented, will become 0, but 0 is greater than or equal to 0. Nums of 0 is the first integer that I have provided from the keyboard, which is -1. And that's it. The last value of I is -1. That's not greater than or equal to 0. So the for structure will be over. And it will go to line 24. Next up is the native C programming language const character array, so the const string type in the C programming language, which has the signature char pointer. You define it like this. You go the name of the local variable, char array, and then you provide either a string literal or an array of chars. And then the size of the char array will be, in this case, for Robert, will be 6. So index is from 0 to 5. And for this thing, Frost will be 5. Index is from 0 to 4. This \0 will end the string and will not be part of the string. So let's actually look at what's happening. Okay. So last, wow, actually has a \0 inside. And that's an interesting thing. I have never seen such a thing before. Okay, whereas first has a \0. Okay, so both are 0 terminated, null terminated. Okay. Last is Frost, so this thing. The null terminator will not be printed. First is Robert, the null terminator will not be printed. strlen of last is 5frost. So strlen stops before the null terminator. The same thing for first, which is Frost. First, which is Robert. So it's 6. Okay, so both of these are null terminated strings. You usually declare a const char pointer like this. Next up is C structs. So these are records or structs in the C programming language, which is a container. Each element has a name and can be of any type. This is stored contiguously on the hard disk, in RAM, in random access memory. Okay. So there will be 16 chars, which char is a byte, 16 bytes, then 11 bytes immediately after the first 16, and then 4 more bytes from the integer. And that's going to give the size of the structure. There's size of, which gives us the size of a struct. Okay, so this is similar to a SQL database table. This would be the structure of the table and one item of this type would be a row in the table. This would be the names of the columns. This would be the width of the column, the type of the column. Let's run with the debugger. Okay, so we declare and initialize a local variable named h1 of type struct header. You must use the keyword struct here when you define it. So the first is Mark. The last is Maguire with a \0 terminator. So there's Mark, \0 terminator, and then the rest are might be anything. The rest of the values. So this is an array. Each of the elements in the array is of type char, which is 1 byte. And the values that are stored in the array are uninitialized by default. And then we put M uppercase, which is integer 77, A lowercase, which is integer 97, etc. The final one would be \0, where we tell the C programming language that this is all we're interested in, Mark, not the rest of the uninitialized items in the array, in this array. Okay, then we have a struct that we have defined. It's a local variable, but it's not initialized, neither the first, nor the last, nor home runs. Okay, so this is an array of type char, 16 bytes. It's a contiguous region of memory where we write this thing, SOSA \0. So uppercase S, lowercase o, lowercase s, lowercase a, and then a \0. After this operation, the array looks like this. So 83, 111, 115, 97, and then a \0. The rest might be uninitialized. Okay, so let's look at first. Not initialized. There's all sorts of junk in here. So on the first position, there will be an uppercase S, then a lowercase a, lowercase m, lowercase y, and then a \0 terminator. So first, uppercase S, 83, lowercase a, 97, m, 109, 109, 121, and then \0. The rest are junk. In order to find out why uppercase S is 83 integer, we want to look at the ASCII table, which is, there's a page for it, a web page, which takes you to this image. So let's find uppercase S with red on the red column. So this one, uppercase S character, is decimal 83 on the decimal column on the row with uppercase S. Okay, lowercase a is this row, so decimal 97, and then is 109, and then lowercase y is 121, and \0 is this guy, decimal 0 null character. Okay. H2 home runs does not have an initialized value, has junk in it. So we put in there a value that's initialized, which is h1.homeruns, which is 70. 70 minus 4, 66. And we store this value in h2.homeruns, 66. And it says in here. Okay, h2 homeruns. Then it's going to print. So this is just a character that needs to be printed to the standard output, doesn't have any special meaning. The hash character, the pound sign, then 1 printed as is, space printed as is, equals printed as is, space printed as is, open curly bracket printed as is, but then %s is a placeholder, goes and reads this, which is h1.last, which is hitter. No, h1.last, which is Maguire, so it writes Maguire, stops before the \0 before the null terminator, then prints a comma that prints a space, so these two things. Then %s is a placeholder for h1.first, which is mark, writes mark and then does not write the null terminator, writes comma and space. %d is a placeholder for home runs, which is 70, writes a 70, then it writes a closing curly bracket and then advances to the next line because it wrote the new line character to the standard output. Okay, the same for writing the entire structure h2 to the standard output to the console, and then program exits successfully. The next program is even more complex, uses structs, but has two types of struct. There's the struct that we saw previously, so hitter, which is probably a baseball thing, last being the last name, first being the first name, so that would be last Puth, right? First Charlie, home runs 20, year 1990. And then many of these structs are used in this array plus a count of players and makes up a bigger structure which is named Hall of Fame. So inside of a struct you can have integers, but you can also have char arrays, which are chars, which are strings of a fixed width or fixed length, not of a fixed. Okay, and then you can also have arrays of other things than the char type. In this case, it's an array with 10 positions, 0 through 9, and on each item in the array, there's an entire struct put in there. So this is a contiguous region of memory, 16 bytes, contiguous region of memory, 11 bytes. This is a contiguous region of memory, 27 bytes. Then this is 4 bytes, 4 bytes. So in total in here there's 27, 31, 35 bytes. So this thing is a contiguous region of 35 bytes. And this is a contiguous region of 350 bytes plus 4 more bytes. This is a contiguous region of 354 bytes in memory. Okay, let's see how everything works. We defined a local variable of type the bigger struct, the one with 354 bytes in size. And we say that there are 0 players in the Hall of Fame. Okay. Then we say HR dot players. So there's 10 possible positions in here, and players starts with 0. So on the 0th position in this array, we put last, first, and home runs and year. The integers we just assign, so these two. The char pointers we use strcopy, such that we take this character, put it on the first position on the first char, which is a byte, and then we take up lowercase u, put it on the index 1, and then put t in here in index 2, h on index 4, and the null terminator, a \0 on the next position. Okay. After these 4 lines, 24 to line 27, the first player in the Hall of Fame will be initialized correctly. Let's look at the entire Hall of Fame. So HR, expand, and players is 1, which is this surprise here, surprise move, where n players is incremented. And then players has random data, with the exception of the first item, which is index 0, which has all of the data populated by us. So first is babe and then \0, home runs 60, last Ruth and then \0, year 1927. Okay, so that's how the first player was added. The exact same way the second player is being added and put into the index 1. And then n players now is 2. So index is 0 and 1. So you take a for loop with index I, goes from 0 to less than 2, which means 0 or 1. We increment it, and this is how we print an entire player. So you go players of I. In this case, I the first time will be 0, so hr.players is an array. hr.players of 0 is the first item in the players array. And then this is what we have access to. So we can go dot year to get here, dot last to get here, dot first to get here, dot home runs to get here. And integers, home runs, and year are going to be printed with %d. And strings, which are last and first, are printed with a placeholder %s in the printf domain-specific language. So again, this is an entire programming language in itself. Okay, so I0 prints the entire struct in player's position 0. and then I is 1 prints the entire struct in the player's array position 1. I is now 2 and I and 2 is not strictly less than 2, so the for repetitive structure finishes. Okay, so after you have a struct, you access its members with dot notation. Next up is the function, the C function example, the first one. We have declared a function which returns a float. The name of the function is average, has two arguments or parameters. The first one is integer, the second one is integer. The first parameter named n, the second parameter named m. What it does, it takes the two integer parameters, does integer addition, and then the result of the addition is divided by 2.0. Why 2.0? Because it wants to do not integer division, but float division. If one of the two operands of the operator slash are float or double, then the division will not be integer division. Instead, it will be floating point division. So division with decimal dot. And then the result, which might be an, so if you go n is 2 and then m is 4, 2 plus 4 will be 6, divided by 2 will be 3.0. If n is 2 and m is 3, the sum will be 5, divided by 2.0 will be 2.5. And then that value will be returned. Let's look with the debugger. We should enter using the keyboard the first and second number. Enter the first number. Let's go with 2. Enter the second number 4. And now we have a use for this button, which is step into. Debug step into F11. So we'll press the step into button once. Because on line 19 we call the function printf, but the function printf has two arguments. The first one is a string literal. The second one needs to be evaluated before printf itself can do its thing. So this avg of x and y will be actually replaced with a float literal. We do not know its value yet. So x is actually 2, y is actually 4, avg of 2 and 4 is going to be 3.0. Let's see how that works. So 2, 4, 2 plus 4 will be 6, divided by 2, 3.0. We're on line 7, will be then on line 19. Oh, line 20. Here we can see that 3.0 has been returned by avg. And then we print it to the terminal, to the standard output. So the average is, this thing is, these characters are printed as they are, the average is. and then %.2f is the placeholder for a float. In our case is 3.0000, but it's written with just 2 decimal positions after the decimal dot. So it's 3 dot and then 2 integers, 2 digits. Okay, 2 characters from 0 to 9. And then a \n, which is the new line character. After that, the process ends successfully. The second example of C programming language functions. There's a function defined which is named print_ins, does not return anything, receives an array. This is the usual way that we pass arrays in the C programming language. So we have the type of the elements in the array, the name of the array, and then the fact that it's an array. And we also need the count of items in the array. So a pair of, this is actually a pointer to contiguous memory, and then this is the number of items in the array, because we know the size of each item in the array. It's 4 bytes. So using the type of the array, we know exactly how much space in memory one item takes. We know size of one item in the array. Again, it's int, which is 4 in my case. And then 4 times n, we know where the block of contiguous memory starts from, because we have a pointer to it, and we know where it ends, because that's 4 times n plus the position where it starts, because we have a pointer to it. We'll see at pointers how these things work. Let's actually run in the debugger. We have an array with 5 elements. Okay. So elements 9, 0, 2, 1, 0. And then print_ins is it calls the function that we have defined on line 5. Again, we need to step into. If we do not want to forget to step into, we can put a breakpoint at the start of the function print_ins. So if n less than or equal to 0, there's nothing to do if there's no elements in the array. It will exit the function immediately. This is called a return early. If we've arrived at line 10, then it means that n is greater than or equal to 1, which means there's items in the array. There's actually no need for this return early, because the for will not do anything if I is 0. But it's a problem if I is negative. No, if n is negative, I'm not sure. So if 0 less than -1 will enter here, but it's not. So this thing is totally not needed as far as I guess. So lines 8 and 9 could be just deleted and the program will work just the same. Okay. This will print an array, goes from 0 and stops before the size of the array, which is indexes in the array, prints using printf all of the integers in the array, but then also puts commas between elements. So there's no need to put a comma before the first element. That's why it skips. If I is 0, will not write a comma. But if I is 1, it will print a comma. Okay, so it printed the elements in the array, comma separated. And then it finishes. Next up, it says that a block that's defined and contained between curly brackets. This is a block, this is another block, this is another block, might have the same variables with the same name defined in it, such as in here, in this innermost block, we have the integer variable with the name I, whereas in the parent block, there's another local variable defined, again of type integer, again with the name I, but this variable is different from this variable. So this is one variable, this is another variable. And this is a global variable. So there's 3 different variables of the same type, int, and with the same name, I. So this variable is this variable. This variable is this variable, and this variable is this variable. This is called a scope, and scopes are useful to have variables defined in here not visible outside of the scope, and also for cleanup. If you define in here a variable, the memory that's defined for it might be deallocated if the allocation is on the stack when you exit the scope where you defined the variable stack allocated. Okay, let's build it. It complains that I should put a return type for the top level entry point C programming language function main. That should be void because it doesn't return anything. Let's run with the debugger. We already have the variable I, which is 3, and it's a global variable because it's available in the main function. And if we had different functions defined, this variable would be available there also in this file. Okay, so we immediately print on line 11 this 3 and then a new line. Okay. Then we use this y as a count. And then we have the second I, which is 99, which will immediately print. And then we have the third I variable, which has the value of j, which is 1, which will immediately print. Okay, then j will become 1. I will be still 99. I has the value of j, so the third level of I variable has the value 1, which we print. J becomes 2, which is the maximum value possible because the outermost I is 3, so only 2 is the last variable, the last value that's strictly less than 3. We print 99 and then we print 2 and then that's it. So this 3 is this one, this 99 is this one, this 0, 1, 2 is this loop. Next up is an example with two C programming language source files. So there's file1.c, main.c. These are translation units. The C compiler will compile each individually. So it will compile file1.c to a file, in my case, that's named file1.o. Will compile main.c to a file that's named main.o. And then at the final step, it will take the two .o files, combine them together in a phase that's called linker, and it will generate the final executable, which is called proj, in my case, P-R-O-J. Okay, let's look at the source code of these two files. The most important file is the one where the C programming language entry point function is defined, which is named main, returns integer, returns 0 success always, and takes no parameters. So let's start looking at the source code from this file. The process starts and it will execute line 5, which does nothing. Line 6, which says, be aware there's somewhere defined a variable that's named I, that's of type integer, and is not defined in this translation unit in main.o, but somewhere else. Then at line 8 says, be aware there's a function named get_j, which takes no parameters and returns integer, that's defined somewhere in some other translation unit than main.o. And then it increments this thing, which we do not even know its value. And then it calls this function, which we do not know the body of yet. And then it finishes successfully. Okay, so this translation unit has all of the code necessary for it to run, but it depends on two things that are defined in another translation unit. There's somewhere a variable named I of type integer that has some value, which we're incrementing here. And then somewhere is defined the body of this function getJ. We could have written extern int, but extern is optional for functions. That's why extern was, the keyword was omitted from line 8. Okay, so the compiler knows how to turn main.c into main.o. And then for this file, file1.c knows, the C compiler knows how to convert file1.c into file1.o. And then it's up to the linker to take symbols defined both in file1.o and in main.o and combine them together. So it will say, how many translation units are there? There's two, main.o and file1.o. Is there a body for the function get_j? Yes, it is, in file1.o. Great. we need to increment this I. The linker will say we're inside the translation unit main.o. Is there any other translation unit available in here where the value for this I variable is defined? Yes, there is. File1.o says that the value of the variable I is 10. Okay, so that's how the compiler and the linker works. And we can see some of the specifics. So we have a 0 variables defined in here. In this translation unit, we're using the variable defined in the other translation unit. The syntax to expose a variable defined in this translation unit to all of the translation units and to be visible to the linker is outside of all functions. You use the simplest syntax possible. So type name, space, variable name equal, and then you give it a value. If you want this variable to be available only inside this translation unit, but to all of the functions, then you must say static. Static is a C keyword that has multiple functionalities. One of the functionalities is that if you're using static when you're defining a value, a variable outside of all of the functions, so on top level in a file, then this will not be made available to the linker. Okay, so what's called a private function, private variable, or an internal variable. Okay? By not specifying static, you make the variable available globally, not only in the entire file1.c, so in the entire translation unit file1.o, but to any translation unit from this current project. And the same with function definitions. All of the top level functions are available in the entire translation unit file1.o, but will also be available to the linker. Okay, let's put a breakpoint in here, a breakpoint in here, and let's start. Okay, first of all, let's look at the value of I. It's 10. Why is it 10? Because it's 10. Go to definition works correctly. Control click on the I and goes not here, but where it was actually defined, which is here. This is a forward declaration. This just specifies a bit the type of the variable, but where the variable is actually defined and is assigned a type is here on line 3, file1.c. And the same, this is a function forward declaration. It's just the signature of the function, not the body of the function. The actual body of the function is here. Okay, my integrated development environment Qt Creator, when I control click on a symbol, will go to its definition. Or we have right click, follow symbol under cursor. Okay, F10. And now I have a breakpoint inside of the body of the get underscore j. It will go there. J is 20, will return the 20, and then it will print the 20. And then the process finishes. Next up, we have a stack. And a stack is similar to, I don't know, a magazine that looks like this and has a spring in here where you can put one item. That's the first item that you put inside. And then you put a second item, and putting item inside of the stack is called push, because it actually shrinks the spring. When you put a third one, you're pushing the stack a third time. Okay, so this is the operation of putting inside. It's pushing, and when you put out, that's popping. That's a pop. And down, it's a push. Okay. You can, when you pop, you always extract the last item that you put inside. So item 3 will be the first to be removed, then item 2, then item 1. This structure is called last in, whatever, what's the name? Last in, first out LIFO. Okay, so the last in was the item number 3. That's the first to come out. Let's look how it's implemented in the C programming language. In this example from the Thinking in C book, there's 3 functions. We have a .h file, we have a .c file. Let's collapse all of the definitions, and a main.c file. Let's start with the main.c. Let's run with the debugger. So there's a for which will push on the stack the integers from 0 to 10. Okay, when does it finish? So now I should be 11. If there's an error, you write to the standard output that there's an error, and there's an error. The last element pushed was, and then we take from the stack and we do the pop operation to find out the last one in. The last element pushed. So the last in was 9. So we try to push on the stack the element 0, 1 through 10. The element 9 was pushed successfully, element 10 was not pushed successfully. That's why we have a stack error. And we know that we try to push the element 10, and the stack tells us, no, I have no 10 in here. The last one that you push successfully is element 9. Okay. And then we have the size of the stack, which is 0 to 9, which is 10. 9. Interesting. It doesn't print the size of the number of elements in the stack. It does a pop, which removes the last item that was pushed on the stack. So this last item is being removed by doing a pop operation in here, and we're printing the value. So the last item was the integer 9. By doing pop, we get it out of the stack, and we write that integer 9, and now the element that's on top of the stack is the element 8. That's why we're using a while repetitive structure. So we get an 8 up until 0, including 0. Okay, now the stack is empty. There's 0 elements inside it. That's why this thing will not will be 0, and the while repetitive structure will be done. Okay, puts a new line, and then we look at if there's errors, and if there's no errors, no errors. Okay. So this is how the stack was actually called. We called all of the functionality of the stack. We have the pop function, which removes the topmost element in the stack. We have the stack size, which tells us how many items are on the stack. We have push, which writes elements on top of the stack. And we have something that tells us if there are errors. In this case, the stack is only 10 elements deep. The 11th element, the integer 10, could not be pushed on the stack. That's why we have the error. Okay, let's see how these things are implemented. So STK push, STK error, STK top, STK size, STK pop, and STK error. STK top. Okay. All of these are functions, C programming language functions. These are their definitions. So functions in the C programming language have a name, a list of parameters, a return type. So this is just the signature of the function. The body of the functions is defined in here. So this is the body of STK error. This is the body of STK size. This is the body of STK top. This is the body of STK pop. And this is the body of STK push. Okay, so this is a contract. This defines the entire signature of the stack as a whole, and then inside of stack.h you might implement these functions any way you want. You might have a backing storage for the stack, as in this case it's a array of 10 integers, or it might be an array of 20 integers. You just change this constant here. So this is the private implementation of the stack, and this is the public interface of the stack. You can change the private implementation any way you want, as long as you keep the same public interface, which is actually a contract that you have with the users and the callers of the stack. So this is a user of the stack. This is the contract of the stack. And this is the private implementation of the stack. Let's see how the private implementation looks like. So there's a storage, which is an array of 10 integers going with indexes from 0 to 9. When we do push, it increments the, this is not actually a pointer, this is a, I don't know, count or something, because it's not actually a pointer. It's an index. A fancy name, so not a C programming language pointer, but a stack pointer in the theory of stacks, not in the theory of the C programming language. Okay, so this is actually an index inside of this array, and error might be 0 or 1. 0 means success, which is the default value. Error is in the worst case scenarios. Here and here. And then there's a public function of the stack that returns the error. So this value is being returned by this function. If this function returns 1, then something went wrong in the stack. If it returns 0, then all of the stack operations were successful. What could go wrong? When you do a push, if there's no more indexes free in the array, for instance, if the current index is 11 or 10, then it's an error case. Okay, or else, if you try to do pop to remove items from the stack, there's 0 indexes left. It sets the error. Okay, so if the index is equal or 0, whatever, or less than 0. It's actually so PTR is actually the count of items in the stack. Okay, we can look with the debugger and see exactly how it's implemented, but the way the stack is implemented is not that important. What's important in here is to look at a C programming language that has so many source code files. So there's a main.cpp, which is called a driver, or the build world, or the caller, and then that's the .h file, which has the definition of a proto class, and then the stack, which has .c, which has the implementation. And there's this separation between the private implementation and the public interface. So there's many C programming language concepts in this example. There's stacks with all of their functionality. There's private implementation, including private data. There's public interface. There's something similar to classes and objects. There's a driver. There's error handling. Okay, so let's run once with the debugger. So it goes stack push 11 times from 0 to 10. First of all, the count of items, which is this PTR, is 0. So goes data of index 0. So you can use the count as the index for the next item to be written. So it puts the 0, which is the, let's look at the caller. So it goes stk push of I, which I is 1, is 0. stk push of 0 tries to put the integer 0 on top of the stack, so the first item to be written to the stack. So x is 0, puts that 0, and then increments the count to become 1. And it's successful because there's still room in the stack, which is room in this array. Okay, can push 1, can push 2, can push a ton of things, including 9. But then it fails to push the 10. So this is 8. This is 9. So this is the last that's still successful. 10 will not have room in the array. Okay, I now is 10. PTR is 10 and it's not less than 10. So this condition is false. Goes and executes the else block, sets the error status to be 0, to be error. And now if we ask, were there errors? It will say yes. Okay, error is set to 1, which means there's errors. This returns 1 if of 1 is successful. Only if of 0 is false. Anything that's different from 0 is Boolean, is similar to Boolean true in the if evaluation. Okay, so puts writes to the terminal this string, stack space error, and a new line. Okay, the last element that has been pushed is not 10 as we had expected, but 9. PTR is 10. So the count of items in the array is 10. The array is full. And this is the way we get, if we know the count of items in an array, this is the way that we get the last item in the array. So count minus 1 is the index. Okay, so write say 9 in here. And now it says, while the count of items is greater than 0, we will remove items from the stack using pop. So size is 10. Does a pop. So this is 10 with minus minus, gets to the last item in the array, which is index 9. And x has the same value as the index on 9. PTR has been decreased, so the count of items is now 9, not 10. The size is now 9. Not what's important is that 9 is greater than 0. PTR, which is the count, is 9. And then this will decrement the count to become 8. Returns 8, prints it, etc. By removing the breakpoints inside of these two functions, stk size and stk pop, the debugger will step over those. So now we're inside main.c all of the time. We don't keep entering from main.c into stack.c file. Okay, writes a new line character. There were no errors. Error is 0. So it writes no stack error and finishes successfully. Next up are variables which, although they're defined inside of a function, so they're not on the top level, outside of all of the functions, they behave like such variables. So this thing Let's see how it works. So the exit is the standard output is 1, 2, 3, 4, 5 and success. Build, run, and the exit, the standard output is identical if we run the program and the process. Okay, so these two are very similar. This defines a global variable that is available in this entire file main.cpp and in this entire translation unit main.o, but not made available to the rest of the other translation units. That's why we have static. Like this, it's available to all translation units. Whereas inside of a function declaration, if we have a variable that we prefix with the keyword static, then the variable will be available just in its scope, but this initialization happens just once. Let's run this thing. Okay, so what's the value of n? We don't know. What's the value of I? Something not initialized. Okay, so we have a for loop from 0 to 4, and we're going to call count. What's returned by the function, we're going to print and then put a space. We're inside of the function. N was declared, exists only here, has the initial value 0, and then we go plus plus n, which increments the value of n to 1, and we return that 1, which we then print in here. Just a second. I keep forgetting to add setBuff stdout and null, which I must always do. Okay, so first it will return 0 plus 1, which is 1, which will get printed, and then a space, this guy. But then the second time we enter the same function count, the value of n is not, to n is not assigned this 0. The value of n is remembered from the previous calls of the function count, which is 1. So basically this is like memory across calls of the current function. Okay, now the value is 2. We're incrementing it, it will become 3, etc. So without the static keyword, n is a local variable defined in this scope. It will start existing on line 5 and it will die on line 7. So the variable starts existing on line 5, disappears on line 7 because it was allocated on the stack, and it gets destroyed. So next time when you call the function count, the variable will be declared again. It will be initialized again to the value 0, and then we'll pre-increment it and return 1, and we'll print 1. Whereas if we use static, then during the entire duration of the process, this part is executed just once. The value that's stored in here is remembered, just that the variable is only accessible in its scope. Laboratory 2. We have a float local variable, an integer local variable. We are asked for a real number, which gets stored into the local variable. And then we go that, so the floating point variable has a decimal dot. We do a floating point addition with 0.5. We convert the result to an integer by removing the decimal point and what comes after it. And then we print the value of this integer, which is the round operation. Let's see how that works. So it says enter a real number, and then I should enter a real number. So let's make that 23.2. X is 23.2 and an 8. Wow. So a ton of zeros and then a random 8 in here. So you cannot store many of the numbers cannot be actually stored as a float correctly. Like in this case, you cannot even store 23.2 on a float because it stores something totally different. Okay, then it goes 23.2 plus 0.5 is 23.7.00.8. And that, if we take just the part that's to the left of the floating decimal dot, it will be 23. So n is 23. And it says that if you take 23.2 and then you round it, it will be 23. But then why does it increment with 0.5? Let's see. If we give it 12.8, then 12.8 plus 0.5 is 13.3. And it takes just the integer part, so that will be 13. So it says that 12.8 rounded is 13. So it doesn't round down, it rounds depending. If it's 12.5, that will become 13. If it's 12.45, that will become 12. So an intelligent rounding. Laboratory number 3. Let's see what it does. Put a breakpoint and start. So there's the sum of odds, the sum of evens, I provided 12, so now n is 12. This is the, and now we need to provide a second number. Okay, let's provide it, 13. Now provide a third number, 14. So what it did, this program, it asked 3 times for an integer, and then it did the same thing. So these lines are identical to these lines, are identical to these lines. So instead of using a repetitive structure, it actually repeated the body of the repetitive structure 3 times. And then we know the rest of the program, where it lists the sum of even and odd numbers. And then a very similar program where the number of integers that we enter from the keyboard might be greater than 3 or different than 3. Previously it was hard-coded to 3, it was always 3. But now it keeps reading integers until I provide the integer 0. So 2. I didn't put any breakpoints previously, so I should have done that. Hopefully it works now. 2. Okay, so 2 is different than 0. It computes if it's odd or even, increments the correct sum. Another number, a 3. And now we're going to provide a 0, such that the execution stops. And is0 breaks out of the repetitive structure, goes to line 29, prints the sums, and that's it. This is another variant of laboratory 4. It repeats forever, not using a while loop, but using a for loop. And then this text is a bit different. Now we're told that by entering a 0, it will stop reading more integers. Put a breakpoint, start. Okay, so enter an integer or 0 to quit. 1. It reads that 1 is different from 0. It computes the fact that it's odd and increments the correct sum. And now we're going to provide a 0 that will execute the body of this then block, which exits the for repetitive structure and prints the 2 sums. Laboratory 5 with structs. There's a struct named employee, so this is a type with members, last name, first name. I don't know what this thing is, either a the job title or the something else. Job title, probably. and then salary, monthly salary. There's a array of employees, maximum 10 elements. Max employees, this 10 is also stored as a macro. So this is similar to a const integer. Let's see what's with these gets. There's no such thing as implicit function declarations. So there's no more gets in the C programming language anymore. That's why, since this source code is just for teaching purposes, we can replace gets with fgets, but then fgets will return new lines, which gets did not. So we'll need to remove the new lines. So ignore this function. Let's look at the main where the important parts happen. So we have 10 employees in an array. These things are not needed. So it writes what I should enter, and then it uses that function to read. So last name, mul, shift F11. Okay, so the employee's last is this mul and then \0, which has a strlen, length of the string, of 4, which is different than 0. If it would be 0, then that would be a signal to exit the repetitive structure 4. So with that, we finish entering employees. Until we do that, we need to keep entering data about employees. The first name, John. Title, sculpture. And salary, 100. And then when it says enter last, we're going to press new line. What did we do? Let's run it without the debugger. That's what the program actually does. It reads at most 10 employees, stores them in the emp's local variable, which is an array of at most 10 structs of type employee, reads one by one the members of that structure. So last, first, title, and salary. At the end, it knows how many, knows the count of employees. the count is incremented in here. And we use a for loop to print one employee at a time. So this is one sprint statement with 1, 2, 3, 4 placeholders, and these are the rest of the parameters of the print function that will be evaluated. This will be evaluated to a verbatim to a string literal and will be replaced here. So this A. And then this is JOHN, and this is tester, and this is the decimal integer 100. Next up is laboratory C, where we have similar source code as before. We still have an employee with last, first, title, salary struct. Maximum employees is 5, not 10. And we have a function to read and add an employee to the emps array. We have an employee public interface. We have an employee.c private implementation with a function that can print the employee with a given at a given index, a function that returns the count of employees, and a function that reads from the terminal, from the keyboard, data about an employee and adds it to this array of employees, maximum 5 employees. The source code that actually reads one employee is the same as previously. Let's put a breakpoint and look at main.c. Now it's way cleaner. There's a while loop that reads and a for loop that prints. Okay, so while has a condition, and this is both a payload that does a ton of things, but then it returns the result. -1 means that no more employees could be read, the array is full, or that the user does not want to add any more employees. Otherwise, it returns the count of employees. Okay, so that's why main.cpp goes if not -1. So -1 means that the user does not want to add any more employees, or there's no more space in the array. And since the actual payload is part of the condition of the while, there's no need to have any block for the while. That's why it's this semicolon to signal that there's no instructions as part of the while block. Otherwise, this entire for would be part of the block of the while. Okay. How does it add employees? So the count of employees starts at 0. It reads the data that needs to be stored in the struct, so starts with last. Title. And then salary. and then back in add employee. This time we're going to not provide a last name, which hopefully will end reading data. And now we have an array of employees with just one item, which we know the count of items using the function num employees should return 1, which it does. And then we call the function print employees, which does what? So if the index is greater than 0, why greater than 0? Why couldn't it be 0? So this is, oh, if it's less than 0 or greater than the count or equal to count, then that's not a valid index and returns an return early. This is the not happy path, and this is the happy path. So we're in the happy path. I is 0, which is less than count, which is 1. This is an NEMPS, number of employees. It prints all of the elements in the struct and returns 1. It returns 0. Okay, and then puts a new line. There's no more employees, so num employees is 1, I is 1, 1 is not less than 1, and the execution finishes. Next up, employee 2. We have again 3 files. Employee.h is the public interface. So for an employee, we can print the entire employee, set the salary or get the salary, get the last, set the last, so setters and getters pair. And there's the constructor create employee. The signature of the struct is the same. And then from main.c, we do not read the employees from the keyboard. We populate them like this on lines 14 and 15. If salary is different than 61, we'll set the salary to 61. Creates another employee. This time uses setters and getters. Adds the employee. And then prints. And it uses free because why? Because the constructor calls malloc, the C programming language function that allocates memory. Let's look at the entire source code in the debugger. So we have an array of employees that can have maximum 5. And what we store in here is pointers to the struct. Okay, then we have one employee pointer, which is returned by the create employee function in here. Okay, So we go into create employee shift, which is this, step into F11. It allocates contiguous memory of the size of this struct, which is 16 plus 11 plus 16 plus 4 bytes. If allocation was successful, then it copies the characters from this string to this array, strcopy, a function in the standard library that copies character by character from one const char pointer to another char pointer. Okay, so this is the string literal mental, this is the string literal Mickey, string literal outfielder, and the integer 58. The employee was allocated in the a continuous chunk of memory. On the bytes of that memory, the correct values have been written. Now the employee looks like this. So Mickey \0 and then some random things. Mental \0 some random things. 58. Outfielder \0 some random things. And this newly allocated pointer is being returned. So the result of malloc is a pointer to a contiguous memory block, and then that pointer is returned. And the value of that pointer is 0x558, etc. Okay, we do the same thing for Roger, Maris. Another pointer is being returned. The two pointers are being stored in EMPS. So EMPS has just two pointers, 0x558 ends with 2A0 and 0 times 558 ends with 2AE0. Okay, the number of employees is 2, minus 1 is 1, so this is the index of the last item added to the amps array, which is this guy. Salary is 60, so salary is not 61. So we change the salary to be 61. Let's go back, amps, last one, salary is now 61. Creates another employee with empty strings and no salary, or 0 salary. Then it uses these setter functions. If the employee exists, so it's not the null pointer, then it copies all of the characters from this const char pointer, which is the string literal AL in this case, into the first, which is a buffer of characters, of bytes. So writes an A, an L, and then an \0 terminator. Okay, AL \0. Null terminator for strings. EMPS now has 3 elements. Number of EMPS employees is now 3. And it prints the employees in the order that they were added. So mental Marys, and then keyline. If the pointer to the employee points to an employee, not to nothing, so pointers can have the value 0, which is the null pointer, or null PTR, or NULL, like this. Or this guy, where are you? Null PTR. So it prints like last time with 3 placeholders of type string, these print parameters, and then 1 placeholder of type integer, this print parameter, enclosed in curly brackets. Okay, and since we allocated memory using malloc 3 times, once, twice, third time, we'll need to call the pair function. So the malloc function has as pair the free function. This frees the allocated memory. You just give it a pointer, and then it computes from the... So a pointer is actually the address of a continuous block of memory. The C programming language knows the size of this expression. It's actually size of this expression, like this. And it frees the memory, it liberates the memory starting from that address up until the last byte that was allocated for that pointer. So for that contiguous block of memory. So from the start address plus until the start address plus size of this expression, which is actually size of employee, which is 16 plus 11 plus 16 plus 4 bytes. Okay. And that's it. So it wrote the 3 employees, it freed the memory for each of the employees, and the process has finished. Next up, it's pointers to pointers. This is multiple instructions on the same line separated with comma, which is something that you should never do, and I never do such a thing. So let's actually rewrite this thing. Hopefully everything stays the same. I didn't change anything. Okay, so now let's put breakpoints and see what's really happening here. First of all, it defines local variable type integer named I with the value 7. Then it asks where is in the memory this 7 variable actually stored, takes the address of that thing and stores it in this variable IP. Just a second. I forgot to call setBuff. So it takes the address of the variable. This allocates for bytes in the memory. On those bytes, it writes a ton of zeros, and then whatever is the base 10 7 represented in base 2 as, which is which. Let's compute that thing. So 7 in base 10, and then there's 7 in base 2. So 7 is 4 plus 3 is 4 plus 2 plus 1. Okay, so that means a 1 and a 1 and a 1. So 2 at the power of 1, 2 at the power of 0, that's 1. 2 at the power of 1, that's 2. 2 at the power of 2 is 4. So in memory, it looks like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, and another one. So 4 bytes. All of the bits are 0 except the final 3, which are ones. Okay, so there's somewhere in the memory such a chunk of bits, continuous memory allocation, and then they have a location in the memory. That location is an address, and that address in the memory is returned by this and stored in here. So this is a local variable named IP, and its type is the address of a 32 bits in memory. So it's a pointer to int. Okay. That thing, we can't easily inspect it. Not sure why. And then we can take the address of this thing. So this is also stored on on 4 bytes in an integer, if that's the size of pointers. Or even more because I'm on a 64-bit machine. So it's 8 bytes, not 4 bytes, the size of a pointer to integer. So the size of pointers on my machine is 64 bits because that's how my CPU is 64-bit. AMD 64, Intel x86 64. Okay, so integer, the size of integer is 4. So 32-bit, 4 bytes. That's how much an integer, that's how many bytes an integer takes in space, in memory. Whereas pointer to int is like any pointer, 64 bits. Okay, so this thing is 64-bit. This thing is also 64-bit. Okay. And then it says that the address of IP contains 7. So somewhere in memory we have these 4 bytes, 32 bits, and the variable I has that value. Then you compute the address, the pointer to this block of memory that's going to be 64-bit, and across different runs of the program will have different values, but it's this thing. So the address in memory where this thing starts is this very large number. So this is hexadecimal, but converted to bits is very long. So this value is the address where this thing has been allocated in memory, where it starts. It's actually the address of the first byte. And then we take a second address that points to this value using the operator ampersand, which gets the address of, and then the opposite of this operator is the dereferencing operator, which takes, in this case, a pointer to a pointer, and then does the reverse. So this is a pointer to a pointer, so it dereferences once, gets to the address of this thing, of this byte, and then dereferences twice and gets to this byte. And then we know that deep down everything points to an integer, so that's being widened to 4 bytes. This thing is being read from the memory and printed in here with %d. So this is not special. These characters are not special in the print domain specific language. This means new line, and this means look at the next parameter of the print function and convert that thing to a decimal signed integer. And that's 7. Whereas %p means print it like this, like a pointer. This is also printed as a pointer because it's a pointer to a pointer, and you dereference it just once, not twice, to get to the 7. Next up, we're doing arrays and pointers. This is an array allocated on the stack. And then we're calling the function mean with a and 5 as parameters, where we're passing an actual array. So we're passing a pointer to the first item in the continuous memory, which is the array, and then the number of items that actually exist in the array. So let's see how that works. We did not specify the size of the array. This is the way you define arrays with a fixed size, or arrays are fixed size. Arrays are located on the stack. The size of A is 5. The type of A is actually int of 5. Has 5 items, these ones, integers, positives. And then we call the function printf. This is a string literal. And then it will need to compute mean of A and 5. Since we have a breakpoint inside of the function mean, it will go there. Step over, actually stepped to line 6 from line 19. Okay, so it takes this A and this 5. What are they? So 5, this is a integer. That's hard-coded here, an integer literal. Whereas A is actually int square parenthesis 5. And still it's passed not at int square parenthesis 5 or int square parenthesis, but as a pointer to an int. So as the 64-bit pointer address to a byte. And then we have the count of items in the array. Okay, so this pointer to an integer is in fact one such thing that points to the first byte, to the first integer in here, to this 56. Okay, and then nums is a this thing, an address. You go nums plus size. I'm not sure what it tries to do. So this sounds like pointer arithmetics, but then you need 4 bytes in here. Not sure what this thing does. So it's pointer arithmetics, and the C programming language knows that this thing is not 1 byte, but it's an address to 4 bytes, to integers. I don't know. Nums continues to point to the first item, which is being dereferenced here. So this is the address of the first integer in the array, which is 56, dereferenced here as the integer 56, stored in the local variable small. And this says size of nums is size of nums. It doesn't put round parentheses around nums. Why not? And let's add this thing. Small equal. Okay, so this dereference is the first. The address gets us the first number, which is 56. Size of nums. So nums is an pointer, so of course the size is 8. It does pointer arithmetic, so it increments nums by 4 such that the pointer points to the first integer in the array, then to the second integer in the array, the third integer, etc. And end is not the integer 9, but what comes after it. That's why it goes less than n, not less than equal to n. Okay. So now nums does not point to 56, but points to 34. When you dereference nums, it will say 34. And 34 is less than the smallest number yet, which is 56. So now in small we'll store the integer 34, increments nums again, so it was at 34, now it's pointing to 89. Dereference it's 89, it's not less than 34. Okay, now it moves the nums pointer to point to the 12, which is less than 34. So now small will contain 12. Now small will contain 9. And now nums points at 9 and it increments the address by 4 bytes. And now it points past the array. And that's identical to end, not past, not strictly less than end. So this condition is false and it will go to line 13. Returns 9, which is the smallest number yet in the array. Okay. As a C programmer, you must really know how to do pointer arithmetics. But pointer arithmetics for me is a smell. I never do it. If I do it, it's like in one file in a huge project of tens of thousands of files. And with big warning signs everywhere. Okay. And now it computes size of A, which is what? 20. Why is it 20? Because it's a contiguous continuous region in memory. 4, 4, 4, 4, 4, 5 times 4 bytes. That's 20 bytes. That's why it says size of A is 20. And then everything finishes. Next up is function definition. So we have two functions in this main.c source code file. There's the one which we always have, which is the main function, the entry point of the executable of the process. And then we have a second function, top level function, free function, named comp, which takes as parameters two pointers. Their size is always 64-bit and returns an integer. And since we define the function on line 24, we cannot use it in line, where is it? 18, because it's defined after it's being used. So that's why we have this thing, which is a forward declaration. We take the entire signature of the function and we copy it anywhere we want above the line where comp is needed first. And with a semicolon to specify that it's a forward declaration and the body of the actual body of the function is somewhere else. Could be in the same file, in the same translation unit, might be in a different file with extension C, so in a different translation unit, because you do not need to specify extern or function forward declarations or function signatures for the functions that have the body in another translation unit. Okay, so in here we have a array with 4 items. Each item contains a char pointer, which in this case are string literals. We're using the qsort function, which comes from stdlib standard C++ programming language header. This is its signature. And let's have it running in the debugger. Let's look at the strings. So it's 4 items, and each is a char pointer. Char pointer, so it's a pointer to a character. I'm not sure. Let's see what's the size of this thing. So size of strings is 32. What does that mean? It means that indeed it contains 4. For what? So it doesn't contain 4 pointers because one pointer is 8. Bytes. So that's times 4, 32. So it's indeed 4 pointers. That's what 32 is. 4 times the size of a pointer. Okay. Then it tries to compute the number of strings by doing size of strings, which is 32, divided by size of strings of 0, which is a pointer to char, so it's a pointer. So it's always 8 in my case. So count of strings in this happy case, it's actually 4. And it's correct. Okay. Then we call this function from the standard library. We give it as parameter a, let's look at the signature again. So void pointer base, this is a pointer. This is a number of members, number of elements. This is the size in bytes of each element, and then the comparison function. And this is the pointer to the first element in the array. So pointer to the first element in the array, correct. The count of items, the size in bytes of one item, and the comparison function. Okay, so the qsort function takes a pointer to a contiguous array, looks there, sees that there's 4 items, and the size is 4 bytes, gets pointer to this thing, pointer to this thing, and puts them in here, in P1 and P2. Now we have access to them, so it's how and now. And we compare the two strings, how and now, and this function returns -1, 0, or 1, probably. Depending on if these are equal, we return 0. If this is greater than this, we return 1, and this is less than this, we return -1. Something like that. Let's actually look. This thing, c++.com. We do not know if it returns -1 or +1. It just says it returns negative or positive value. 0 in case the two are equal, less than 0 if ptr1 is less than ptr2. So if ptr1 less than ptr2, so if a less than b, then it's negative, otherwise it's positive. If a greater than b. So in our case, a is how, b is now, and how is less than now. So that's going to be a negative. Shift F11, F5. So it enters this comp function a number of times. At the end, this will be sorted alphabetically, hopefully. Okay, let's look at strings now. So brown cow, how, and now. Okay, and now we're printing them. So we have 4 strings, goes from 0 to less than 4, which is 3, and writes those strings and puts a new line. Next up, we take a function, which is this print function defined in stdio.age. And this can be used as a right-hand side because it has a value. And the value is pointer to function. So this is a pointer to a function that has the same signature as print. This is the structure, the signature of print. And here we have pointer to a function that has this type of signature. So returns int and has as parameters a const char and a vararg. So let's look at that too. So int is part of the signature, printf is not part of the signature, it's just the name of the function. Const is part of the signature, char is part of the signature. This is part of the signature, the fact that it's a pointer. This restrict is not part of the signature, the name of the parameter is not part of the signature. And then the fact that it's varargs. So if you take the real signature of the function, in order to obtain a pointer to such a function, you need to add this pointer character. Okay, so we look at the function print, we find it, we take a pointer to it, and we store it in the local variable named fp that has the correct signature, which is a pointer to a function that has this signature and has stored inside of fp the actual address of printf. Let's run everything. So we have local variable I, local variable fp. This fp thing is a 64-bit pointer address into memory, but its address points not to data as it was previously in all our previous examples, such as the first element into an array of integers, but it points to functionality. So not to data, but to functionality, to code, not to data. Okay, and can be called like a function because it's a pointer to function. You don't need to dereference it and then call it. The correct parameters are being provided, so 2 parameters with the print style, domain specific language, %d is the placeholder, this is actually integer. We could have dereferenced it, but it's not needed. And it prints what we expected. So new line terminator here. These 5 characters written as they are, and %d replaced with the value stored inside the variable I, which is actually 1. This is another way of doing what we did previously, which is we're going to define the type. So previously we had inline when we declared the local variable fp, we surrounded this fp with the definition of the pointer to a function that has the signature of printf. Now we define a type, which is the same thing, which is a pointer, this thing, to a function that returns void and has parameters const pointer and then varargs. So this is the signature of printf. You take printf, you cast it to this signature, and then you store in the local variable fp the address to printf. And then the rest of the lines are identical to what was in the previous example. Okay, so f type is actually a type, not a local variable. We have the local variable I, and we have fp, which we know it is a pointer to printf, even the debugger tells us so. And then we're calling so we're dereferencing fp, which is a pointer to fprint. We get fprint, printf, and then we're calling that function printf. Okay, let's actually see that dereferencing is also okay. Let's print 2. A6. Let's print A6. Okay, line 11 prints correctly. Line 12 also prints correctly. So this is a pointer to a function. This is the way we're dereferencing it, and now we have the function and we call the function. But that's not needed because the C programming language does the clever thing, which is this knows that this is the pointer to a function, and it dereferences it automatically and calls it. Next up, we are using pointers and dereferencing pointers in order to look at the actual memory that's allocated. We have this inspect function. We're declaring some local variables and we're looking at those. So we have a local variable named C, which is of type char. So type char means 1 byte, which means 8 bits. And this lowercase a, according to the ASCII table, is, so lowercase a is 97. So let's actually inspect that thing. It's just 1 byte, and the byte as hexadecimal is 61, which is what we see here. So lowercase a character is 97 in base 10 in decimal, and it's 61 in base 16 in hexadecimal. Okay. Then we have short I, which is, I don't know, 2 bytes. There's 2 bytes, one is nothing, and the other one is 64. Because 100 in base 10 probably is 64 in base 16, which is what we're using here. We're writing %02 uppercase X, which means hexadecimal. Okay. Then we have long, which long is the same as what? Is 64 bits and int is 32 bit. You see? So yes, it's 8 bytes, which means 64 bit. Whereas integer is 4 bytes, 32 bit. Then this double is longer than float, which I don't really care how it's represented in memory. And the last one is the string. So the string hello is represented in memory as the bytes HELLO and \0, which have the values in hexadecimal 68, then 65, then 6C, then 6C, then 6F, and then 0. Let's look again at the numbers. So lowercase h, 68, 65, these things. 6C, 6C, 6F, and then the null terminator, which is hexadecimal 0. And that's it. So these were all of the examples written in the C programming language in the book Thinking in C by Bruce Eckel. Thank you.